Okay, so the next turn is for Javier Sabariego. He's going to talk about the monitoring in HPC, in hybrid HPC quantum computing environments. Thank you so much.
Okay. 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 Here it is. Already. Perfect. So, thank you for the welcome. Yes. Today we will be talking about this. So, for structuring this talk, I will try to actually devote a lot of time for motivating this because, I mean, this could be a very, very short talk. We use the Grafana stack, but I want to, I really want to focus on what we will be monitoring. So for that, we will be talking about quantum computing, and we will start again. And I'm sorry, I know that other years we performed like a full introduction on what it was, and we reached simple algorithms. This time we will go the other way around because where I want to reach is to the thing that you can kick. So we will be talking about, yes, the motivation, what we have on our labs, what will you be seeing if you go to the BSc they have there. We will be talking about our software stack, how we organize everything, and finally we will be displaying the diagrams on how we monitor it all. So, okay, this slide, we can die here. Quantum computing, what it is. I was very alert on the other talks to try to skip the pieces that were already presented, and I think that I can really start with for the beginning, because in terms of quantum, they told very fast a lot of things that are really complex. So, quantum computing is performing computations with qubits. Okay, simple enough. What is a qubit? A qubit is a mathematical object, so not real. Is the most simple discrete two-level quantum object that you can do things with. So you want it to be the most simple things because then the building complex things on top of it is easier. It's easy to manipulate. It's easy to build. To mathematically develop things for it. What I mean by discrete two-level is that whenever you ask a qubit on which state it is, it will always answer on one state or on another one. Let's call those 0 and 1s because of standards. Some people call that up and down, depending on what you are talking about. But that's kind of all. Whenever you ask a qubit which state it is, it will answer 0 or it will answer 1. So, quantum object. We have discrete two-level. Okay, quantum object. Quantum object basically for us means that we will be exploiting two properties of it, superposition and entanglement. Superposition is kind of easy. We've said that it has two possible states. Superposition means that whenever you are not asking it, it can really be on any arbitrary mixture of those two states. So if it's always on one state and you ask it what state are you in, it will always answer 1. But if it's in an intermediate state, it will sometimes answer you 1, sometimes will answer you 0, with some statistics given by its properties. Okay, we can leave it there. Now, superposition. If we have more than one qubit, if we have 2 qubits, still simple, superposition means that I will prepare my full system in such a state that if I measure only one qubit, if I ask one qubit, which state are you in, I already know the state of the order. My companion before already presented a Bell state. That's a maximum entangled state across all your system. If you only have 2 qubits, all your system is 2 qubits. So, 2 qubits are entangled. Okay. This is not, and the only key thing that I want to comment about that is that this is not a conditional operation. You are not measuring one qubit and then asking yourself depending on the state of the one you are forcing the other. This is not a conditional. This is an a priori operation. You have set your system such that any collective state that doesn't fulfill this property is forbidden. And this is the complicated things, and this is where mathematically it gets weird, but it's still simple and easy to manipulate. So with that, we know what is a qubit, and I guess that I can convince you that to do quantum computation, you need quantum logics. Quantum logics are easy to explain, and the most approachable way of explaining those is by an extension of the Boolean logic that we have on usual processors. We have a two-level system, so we can perform your usual Boolean operations between 0 and 1s, that's okay. But then we have these two properties, so we imagine, we create two additional logical gates. One is the Hadamard that gets only one qubit and puts that in a superposition state. One is the CNOT that you can use to build the entangled states. With that, I guess that is easy to expect that there are some problems that you have two additional logical gates that cannot be derived from the ones we already have. And we have these intermediate states that we can navigate as long as we are not measuring the qubits, we are not asking what state they are in. Then there will be some problems. Which solution will be faster to arrive to? So, well, that's basically quantum computing. But I'm making this is the most easiest way, and the things that whenever my family asks me what do I do, this is the kind of easy approach to it, because it is okay, you already know normal logic, so extending it seems kind of natural, but it is not the only way of doing quantum computing. In fact, in Qilimanjaro, we do analog quantum computing, which means that we are treating the chips as a whole and only working continuously with the full state of our chip in such a way that it mimics the mathematical problem that you are trying to solve, so that whenever you measure your full qubit, you get the solution of your mathematical problem. Analog computing is actually quite an old thing. Quantum analog, kind of not. And the good thing, if you have a qubit, if you have a chip that you can control precisely enough, the good thing is that you can do both. And that's called hybrid quantum computing. Well, that's one of the things that they do, that they call hybrid quantum computing. It is the ones that we want to explore. It is the ones that we are proposing. And so our setups are able to do this. So one thing more before going to our setups is that if I said that a qubit is a mathematical object, then are there qubits in nature? Yes, an electron with their spin behaves almost, it is the same mathematical object, but if you try to put electrons and do computation with them, you will very quickly see that the spin is not the only quantum property they have, and all of them interact with each other, so it gets messy. What you want to do is to design a system that on a specific ranges of parameters behaves closely enough to a qubit. And this closely enough is the reason why my mate before also when doing no computations on their qubits, so that it didn't behave like, it was only recovering 0.9 of the time the one state, even though they were preparing the one state and doing nothing else. So yes, we can only build approximations to qubits, but with enough control and with enough tooling, with enough technology, let's say, that should be enough. So, how do we expose this? Of course, we have some cloud access for people to send jobs to us that have their description of what the quantum problems they want to solve encode serialized on them. We have the Qili SDK, which is how we are calling the tool that we are actually publishing for designing these quantum operations and for actually simulating them or sending it to our labs. We have the Qili OS, which is the bunch of libraries, daemon, artifacts, whatever that in the end allows you to send the pulses you need to send to the qubits. And then we have the QPUs, the digital ones, the analog ones, and the simulators on CPU and GPUs. Yes. One thing I forgot is that there are many physical objects that you can, when I said that you need to define something that behaves like a qubit, there are many systems that can behave approximately like a qubit. Neutral atoms were mentioned before. If you put a photon between two mirrors, that also can become a qubit. If you put an ion and you trap it with a laser tweezers, that can also become like a qubit. What we do are printed circuits, superconducting printed circuits with loops. And the question that you are asking the circuit is, on a specific loop, is there a current running on clockwise, or is there a current running counterclockwise? One of them is a 0, one of them is a 1. That's the thing you can actually kick in our lab. So, how do we talk with that thing? The setups are quite big. There are a lot of tubes, there are a lot of cables, there are a lot of devices for one single chip. So this looks like a waste of space. We will see what specific parts are here. So, first of all, and maybe the most important, most direct way, the thing that holds the way we directly talk to is the control electronics rack. Here we have, as our chips are, in the end of the day, electronic circuits, what we do for talking with them is sending electromagnetic pulses to them, or electric continuous currents. And the thing is that, well, in the end, yes, you have cables with electromagnetic microwave range waves. And that is kind of all. You need to orchestrate all of them, so you have a source that acts as a clock for them. The resolution you need to operate then is at the nanosecond scale. So all of them need to orchestrate between a common time and all of that. You need to order them, you need to trigger the operations, and then the slowest part is actually retrieving the results. This is done usually with FPGAs. There are many manufacturers, but in the end, the processes are kind of similar. And the steps we have abstracted for that is basically preparing the Q program, the description of your quantum circuits, connecting to all the instruments and setting the parameters that you want to set, compile that to the language of each of the system, and then execute. It doesn't have a lot more than that. Then, the central part, the tubes, the things that are so flashy are actually the cryogenic chambers. The qubit is inside. They are usually structured in steps for different ranges of temperatures. The coldest one, where the qubit is living, is on the millikelvin scale, so 1,000 times colder, well, 100 times colder than the outer space. And the bad thing about this type of circuits is that they are very good sensors for everything. But if you want to perform computation with them, you don't want them to sense anything else than the things you are sending them to. So you need to have a lot of electric isolation, which is very easy with a Faraday, Faraday cage. You need to have very, very good magnetic isolation, which is very weird to achieve, actually. You need kind of exotic materials for that. You need a lot of thermal isolation. Anything that is hot will be emitting photons that will be interacting with the qubit. So not only are you cooling that for getting the superconducting thing to be superconductive, but also for avoiding presence of photons. So yes, those need to be very, very well isolated systems. That's why they are so big and bulky and all of that. Also, the technology for cooling, for reaching that temperature is crazy. There are few manufacturers in the world, and we have setups for 4 different manufacturers of them, which makes the monitoring complex, let's say. And this other part, the part that is farthest from, so this part and this part are where the devices for controlling the fridge are. And these are the ones, let me check the time, yes. These are the things that each manufacturer do on its own way. They all use kind of industrial-ish standards, but each of them chooses their own. They are from different countries, so even the units that they do for measuring their sensors vary from one to another. They are very, very closed, so their documentation is not always the best. And that's kind of what it makes it complicated to do. They are often not necessarily startups, but the technology is very, very novel. So you don't get, as it was said before, the reliability you would expect on a normal computer. So well, achieve high availability of one of those setups will be a problem in the future. With this, these are the devices we want to monitor for the execution part of our problem. So this will be active whenever we are either measuring the qubit for benchmarking it or for executing actual client jobs. This is the thing we want to monitor always because it will be encoding the availability of the setup. If whatever sensor is giving a wrong signal, if the temperatures are not on point or whatever, then we cannot send more jobs. And the benchmarks of the qubits are the things that we want, of the chips are the things that we want to expose, and of course, all the software stack, either for orchestrating the jobs, for exposing, the web applications, the backends are the things that you want to be monitoring. So, at the labs, for the on-prem, for the cloud part, we have some part of our APIs on the cloud, and for that we use the standard monitoring that the cloud provider offers. For the on-prem part, as I said, we use the full Grafana stack. We started only using the dashboards, and then slowly we introduced the rest of tools. So our preferred way, personally, is using a Prometheus for scrapping exporters. It is the simplest, more reliable thing that we have tested so far. And it is a mechanism that, for me at least, it looks like as old as time. It has always been there for me. But I'm very young, I mean, you understand. So we have exporters for everything we can have, ideally maintained by people that know more about the tools, except for one little device that is the WAMP protocol. We will talk about that if we have time. So then the Prometheus is remote writing to a Mimir for long storage for long-term storage of time-based metrics, and then consumed from a Grafana dashboard. For the things that we cannot have an exporter for, either because their nature are different, like logs, profiles, or because we need a parsing tool, because an exporter is not available, we have the stack with Alloy for performing some conversions of data or whatever, and then Grafana consumes from everything else. And for weirder situations where the data is not as well structured or that we need to perform like more steps in the middle, we use InfluxDB's telegraphs that then remote writes to Prometheus, and the rest of the stack is the same as before. In terms of the fridges, I shouldn't talk about which provider is doing what, but I can talk about what we have found in general. So the easiest case we have found is they have an internal computer that offers a web server that you request and you get information back, and that's beautiful. It works, it has never failed. I don't know why anyone would do anything else, but they do. Another provider puts a computer in the middle that then adds a single point of failure. This computer is connected by USB and Ethernet to the same device, which is 2 points of failure also. The drivers are only available for Windows. So, well, that's another thing you need to consider. They have internal MQTT servers, but for some reason they don't always expose. We just discover them. We have that as a backup. And the information is structured, but very, very weirdly. So that's why we have the telegraph here. That is the one that was then remote writing to Prometheus. Then there is another setup that is using the WAMP protocol for delivering messages. This protocol has very, very little adoption. I have slides for explaining it, but I think that we will probably skip them. The good thing about it is that it offers both publish and subscribe mechanisms and get and RCP request, let's say. But the bad thing is that it has very, very little adoption and very, very little community. Almost no documentation for the major manufacturers of that. A lot of broken links on the internet, and it is luckily one of those things that whenever you set up, you don't have to touch again. We had to build the exporter for that inside, and it is working well enough, but I'm not proud of that code. And finally, my less preferred case is a fridge. That what they do is they have a Windows-only process that needs to be always running, also a USB connection, but that the process is only writing logs to a specific folder every 2 or 3 seconds. It writes bunches of few files. Some of them are CSVs, some of them are other formats, and there's not a clear pattern. Units change between one file and the other, and for that we have actually an SSH connection that is copying them to at least put them on a Linux environment, and then some telegraph parsing the information. With this, yes, I had the slides for talking about the WAMP protocol, but I think that I will probably skip them because I want to allow time for the questions. But I have details about the exporter that we built. If anyone's interested, I have not even seen forums talking about this, so I assume that no one's interested, and that's the reason we had to build it. So with all of that, yes, I think that we can leave space for the questions, if there are any. Thank you all for your attention.
Thank you so much. Coming to you.
Thank you. So thank you for your talk. You mentioned at the beginning of your talk that you need to synchronize some elements at the nanosecond scale. Do you also need to monitor at the nanosecond scale some of the components, and how do you achieve that?
No. We don't have to monitor them. We rely on the metrics they release, and that's usually on the millisecond scale. On the nanosecond scale, we will get the results of the measurements that we perform and the data that we can acquire from those devices, from those they are mostly FPGAs. And then the stability metrics of the temperatures that you have on your signal generators, the power that they consume, the CPU usage, the RAM usage. So it's quite your standard measurements of any connected device.
Okay, so well, thank you so much. So please, another applause for